Hi everyone, my name is Apurva Bhasin and I'm delighted to be a part of this conference. I'm here to talk about a new technology, the Virus BioResistor, for the detection of antibodies. An alumna of UC Irvine, I have been part of the tech since 2016 and currently I'm a research scientist at Sagetech, a diagnostic company that is pioneering the Virus BioResistor towards commercialization and clinical trials. The idea to develop the VBR stemmed from the aspiration to provide an alternative to complex and time-consuming procedures for detection of cancer and to aid better prognosis. The assured guidelines for point of care helped us carve out the desirable attributes to be expected and incorporated into the VBR. So here I would like to start with introducing the VBR and its different components. Like a very conventional biosensor, the VBR is composed of the analyte of interest, a biorecognition element, which is the M13 virus, a transducer, and an electrode. The biorecognition element is M13 virus particles, 6 nanometer wide and 1 micron long. These are the unconventional alternatives to supplant antibodies. They are inexpensive and robust. They are composed of 2,700 copies of P8 coat protein, and this virus can be easily engineered to display peptides of interest that are very specific for the detection of the desired analyte. The transducer that wires these M13 particles to the external electronic circuitry is composed of conducting polymers. The upper layer that embeds these M13 particles is P dot, and the bottom layer that connects directly the P dot to the gold electrode is P dot PSS. P dot blended with PSS is conjugated P dot, positively doped, balanced by the sulfonate anionic group in the PSS. And this polymeric blend allows the simple technology like spin coating to be possible on the gold electrodes. P dot is known for its high conductivity, good stability, biocompatibility, and makes an excellent candidate to house the M13 particles. The electrode for VBR is displayed on the screen. The distance between two gold electrodes is 1.5 millimeter. This is connected with a P.PSS layer, and this is where all the magic happens. In short, the virus bioresistor is just a simple resistor whose film resistance changes upon addition of the analyte molecules. The virus bioresistor can easily be visualized in the form of a circuit that is composed of a resistor that represents the solution resistance, two sets of capacitors representing the interfacial capacitance, and the film resistance, which is composed of the virus P dot and the P dot PSS layer. This translation of the sensor to a circuit helps us when we process the data for impedance spectroscopy, which is the mode of collecting data in the VBRs. So let's dive into the fabrication of VBR to check out how complicated or how simple it is to construct a VBR. The device fabrication includes the spin coating of P.PSS layer on the bare gold electrodes. Then this layer is aged in PBS for 30 minutes to get rid of any background signals that can be generated due to the swelling of the P.PSS layer. Once this is done, a solution called the electroplating solution is added, which is composed of the monomer E dot, a supporting electrolyte lithium perchlorate, and of course the phage particles. It is subjected to electropolymerization, which leads to the formation of a P. phage layer, which is slightly darker blue in color. This layer is then washed with the buffer solution, and a fresh solution for baseline reading is added. Let's take a deeper look on what electropolymerization is for these E. phage particles. During polymerization of E. it is oxidized to a cation radical, and radical coupling occurs near the electrode surface until all the resulting oligomers lose solubility, and with anions from the solution to balance the positive charge, they precipitate onto the electrode. Now, the M13 virus particles have a net negative charge as a consequence of three ionizable moieties: glutamine, aspartate, aspartate 5 on P8 coat protein. Polymerization on positively charged P. in the presence of negatively charged M13 would electrostatically promote the incorporation of M13 particles within the polymer matrix. To form this layer, it hardly takes around 60 seconds, and the sensor is ready for sensing. Under the microscope, the scanning electron microscope, you can actually visualize and distinguish between P. films and P. phage films. The P. films alone have these characteristic P. stalagmites, which are also present in the P. M13 films, but we can easily visualize black thread-like structures in the P. phage films. These give us a very good proof that we are indeed incorporating these virus particles into the polymer. The impedance is the mode of detection of the VBR signal. Impedance is defined as the effective resistance of an electronic circuit to alternating current arising from the combined effects of ohmic resistance and reactance. To simplify, the x-axis represents the resistance and the y-axis represents the reactive capacitance. A Nyquist plot is basically represented to collect the background in a buffer, which is recorded from the lower frequencies to the higher frequencies. When the analyte is added to the sensor, after an incubation time of 10 minutes, another Nyquist plot is recorded from lower to higher frequencies. Now, as discussed earlier, this VBR can be easily translated into a circuit. This circuit is useful for EIS softwares, and it helps us to analyze these Nyquist plots in conjunction with the circuit. Once it is fit, we get the RVBR extracted from the circuit, which is a combination of the virus P. and the P. PSS layer. The signal, which is referred to as delta RVBR, is basically the difference of the RVBR recorded for the analyte minus the RVBR recorded for the baseline. So let's discuss VBR as a biosensor. The first version of VBR, VBR 1.0, was formed for the detection of HSA. Now, something to note here is the P. PSS layer, according to the SEM micrograph, was 250 nanometers, whereas the P. virus layer was 90 nanometers. Now, what is important here is when different concentrations of HSA were exposed to the sensor, we could see a clear difference in the RVBR recorded for different concentrations of HSA. Similarly, VBR 2.0 was created for the detection of DJ1. DJ1 is a cancer biomarker, a bladder cancer biomarker. Its size is really small, and it is worth noting, to make this sensor, we used a PEDOT-PSS film that is thinner than the version 1. Now, why did we do that? We realized that PEDOT-PSS and PEDOT, both layers combine to make our film. Now, if you look at the parallel combination of resistors and try to calculate the RVBR, you would know that if we increase the resistance of our PEDOT-PSS, the overall RVBR should increase. This was exactly what we noted when we tried to detect 100 nanomolar of DJ1 across a range of PEDOT-PSS resistances. Now this was magical. We found a switch to increase the sensitivity of the film just by spin coating different thicknesses of PEDOT-PSS. Data was recorded for the detection of DJ1, and impressive COVs. We could replicate the data not only in the synthetic urine, but also in the human urine. We also challenged the sensor for specificity, running a lot of controls, adding a phage that was not specific for DJ1, or adding no phage at all, or adding DL1 phage but exposing it to another protein of similar size compared to DJ1. We also noticed that just like the VBR1, VBR 2.0 was as fast, and it could give us a reliable signal to detect within 60 seconds. So the attributes of VBR were very encouraging. It was found to be specific, reproducible, fast, generalizable, detected two proteins HSA and DJ1. Now, it's worth noting that these two proteins are relatively smaller molecules. So what happens when we want to sense antibodies? As compared to the other two, antibodies are 150 kilodaltons in size. The antibody detection with the VBR version 3, which is also known as the overoxidized VBR, was tested with two different antibodies. We chose M13KO7 phage for anti-M13 antibodies. Now this phage is basically just a M13 phage without any peptide modifications. So it means that the anti-M13 is supposed to interact with the 2700 copies of P8 coat protein. Whereas the second antibody, which is anti-flag, was supposed to interact with the M13 flag phage, which had the flag tags on the P8 coat protein. So this was a bioengineered phage, as opposed to the M13, which was the phage itself in its pristine form. Interestingly, when I tried to test the antibody detection with just the conventional VBR 2.0, I hardly could see a trend. I could not connect the increasing concentration of signal with increasing signals. So a range of concentrations were tested with the VBR before giving up and trying out something new. So what happened? What did we do to get this red bar graph, which is now perfectly detecting the antibodies? We overoxidized our VBR biolayer. Now, reports of overoxidation of PEDOT are in the literature. So we thought, let's apply those principles to our sensor and see if we can also benefit from this tiny electrochemical oxidation, which proved to be magical for us, and it enabled antibody detection. The fabrication of O2VBR was quite similar, and the only thing that changed was this one step where after the regular VBR film was formed, We added the lithium perchlorate solution again, and we oxidized the film by applying a potential of 0.8 volts versus MSC. It is very easy to note that the color has changed from blue to transparent. Now, this has been reported in the literature because of two reasons. Because of the thinning of the P dot layer, and this is a bleaching which is a result of the degradation of P dot backbone post-oxidation. So we did a sim on these overoxidized P dot films, and we noticed that the top layer was indeed thinner as compared to the conventional VBR 2.0. Well, the good part was that we did still see the stalagmites and the dense virus region in the overoxidized P dot. As mentioned earlier, we chose to overoxidize VBR with electrochemistry, and we applied a potential of 0.8 volts for varying times, 50 seconds, 100 seconds. It is worth noting that with the increase in the time, the Nyquist plots were seen to become more bigger and broader. It meant that the film was getting as resistive as the time increased. Beyond 100 seconds, we noted delamination of these films. To test antibodies directly on a new structure seemed risky, so we decided to go with the DJ1 detection with oxidized VBR first. And we noted a significant signal enhancement, almost 6 times with the DJ1 protein for the overoxidized VBR. Now, this was good news. It just meant that the way we had increased the sensitivity from VBR 1.0 to 2.0, we did the same thing now with a different method from 2.0 to 3.0. ELISA results for anti-flag and anti-M13 were studied, and it was noted that the EC50 lies around 7.6 nanogram per ml. It's a good affinity, and it made me question that the affinities seem to be very similar for both the phage and antibodies. Although anti-M13 has way more binding sites as compared to the anti-flag. Well, we continued and we detected antibodies with the overoxidized VBR. Now, the bar graphs shown here, all of these are individual devices. These error bars on the bars are basically representing 3 scans of Nyquist per reading. The percentage shown here is the COVs. Lower COVs gave us the encouragement that this sensor, even though overoxidized, does not lose its quality to be very reproducible. Now, when you plot a calibration plot for these two antibodies, you can observe that the H value is greater than 1. It means there's a positive cooperativity. Binding interaction is increasing with the increase in binding sites occupied. But another interesting observation is, as opposed to the results from the ELISA, the KD of the VBR calibration curves was different. Now, anti-M13 affinity supersedes the anti-flag according to the VBR results. This makes sense because there are more available binding sites. Now, this ability to distinguish the affinities was blurred in ELISA. To challenge the specificity of the sensor, no phage film, a KO7 phage exposed to different antibodies with no affinity for the phage were tested successfully. The only thing I would like to tell here is we were not able to obtain time scans graphs for this sensor. And the incubation time for these sensors was 20 minutes as opposed to 10-minute incubation times for the VBR versions 1 and 2. We could not ignore the effect that larger proteins produce less signals with the VBRs 1 and 2, and only with the overoxidized VBR could we detect proteins that are large enough, like antibodies themselves. So, how is all this happening? How is this so sensitive? Let's delve into it. If I talk about VBR 1 and 2, we can generally see P dot as a combination of crystalline domains and disordered domains of lower conductivity. And the viruses are concentrated in the disordered regions. So what happens when we look at the transport? The interchain transport within the P dot is basically through interchain hopping, while the intrachain transport happens via bipolarons. The interchain hopping is of special interest to us because that is what gets disrupted when proteins seep into this P dot phage layer due to immunospecific partitioning. So when the target proteins permeate in this layer due to the immunoaffinity partition, the P dot polymeric interchain contacts are disrupted. Now, once these contacts are disrupted, the hopping between the P dot islands becomes difficult. Now, that causes a decreased conductivity or increased resistance that is recorded by the VBR. So what changes when we are working with overoxidized VBR? Well, in overoxidized VBR, despite the fact that we have crystalline and disordered regions, we now also have a backbone of P dot chains which is severely affected by the overoxidation, which leads to broken chain contacts to start with. Now, since there is more of the disordered region, now it becomes easier for bigger molecules like IgG to percolate and settle into these disordered regions compared to the closely packed P dot regions pre-overoxidation. Now the target proteins, which is IgG, they can permeate this layer and interrupt the polymeric chain contacts as mentioned before to create the same effect but with higher magnitude. Let's not miss the point. In summary, we learned that VBR exhibits sensitivity that is inversely related to the size of the analyte. This encouraged us to explore the possibility of electrochemically overoxidized P dot as a sensing platform. These overoxidized VBRs enabled the detection and quantification of 2 antibodies with a detection limit of 40 nanograms per mil and a dynamic range of quantification extending to 600 nanograms per mil. The KD values reported by the VBR suggested that the VBR can differentiate between the binding affinities of the 2 antibodies to the phage. I'm thankful to all these institutions that made this research possible. I would like to repeat that this technology has been developed and patented by the University of California, Irvine, and is licensed to Sagetech Diagnostics. All the images and content in the presentation is based on the following papers. I thank everyone here for listening and for their patience. Thank you so much. Have a great day.